2 long, we can clearly see whatever direction the net force is, that is also the direction of the acceleration. Mass is just a scalar quantity, and it doesn't distort any direction whatsoever. So, if it's accelerating, you immediately know that it's coming from some net force, and vice versa. If there's a net force acting on the object, then it's going to cause acceleration. And so, in terms of the free body diagram, right, we did a few different examples, and that's depicted here. Now, this is going to be the shortest lecture so far because last class it only took 40 minutes. That's because I was just looking at how much I would get to. So today's going to be lecture. Then next Monday will also be lecture. Remember that? Okay. And then next Wednesday will be the exam, as well as next Thursday. If I did a full lecture today, as well as a full lecture next Monday, that means after your midterm, you're not going to have a quiz, you're also going to have a short exam, which I don't think that's what you guys want, because that's the amount of material that will be covered if I did a full lecture today. So what I want to do right now is pretty much this. I just want to do 2 examples, and we'll cut the quiz at that this Wednesday. Okay. So we're just going to do 2 examples and then call it a day, and that took 40 minutes for the calc-based section. Okay. So let's pick up here. Now there was a few things that I did want to at least recall to your mind before I did the the examples. So what we're going to be looking at is actually dynamics along a line. Meaning this is one-dimensional dynamics. Just like how we started off kinematics with 1 dimension, because that was the simplest scenario, we're going to do the same thing here. Before we get to those examples, let's recall this concept of equilibrium. Equilibrium. That condition is when the net force is equal to 0. So if the net force is equal to 0, then you get what is called, more specifically, mechanical equilibrium. You guys remember that? Now I want to recall you guys to this because I want to tell you guys specifically, what does this actually mean? Because the net force, well, this force is a vector, they have the x and y components. So we have F net x and F net y. At equilibrium, what is F net x and what is F net y? There's only one way for the net force to equal 0, and that is only if both of these components are also equal to 0 at the same time. So the net force vector equaling 0 means the individual components are 0. The x and y components are 0 at the same time. So this must be simultaneously. They must simultaneously be equal to 0. Now, just for completion, I'm going to write the net force in its full form. F net is going to be F net in the x times the unit vector I plus F net in the y times the unit vector j. So you're in mechanical equilibrium when this is true. Well, how are we actually going to be seeing that written inside a problem? So let me tell you the various scenarios which will hint at it being in equilibrium. It is in equilibrium if F net is equal to 0. That also means acceleration is equal to 0. And that is through Newton's second law. What was Newton's second law? Huh? Newton's second law? Yeah.
F net equals mass times acceleration.
Yeah, F net is equal to mass times acceleration. So if the net force is equal to 0, what is acceleration? Also equal to 0. So if the problem statement says there is no acceleration, it's in equilibrium. Well, what does acceleration equal to 0 actually mean? That means velocity is constant. That is another indication that you are in equilibrium. Right, all of these mean the same thing, but velocity is constant means acceleration is 0, which means through Newton's second law, F net is equal to 0. They don't take equal number of logical steps though. So, if you're given in the problem either one of these scenarios, you immediately know that it's in equilibrium. And of course, lastly, it's in equilibrium if the problem simply says so. Problem says equilibrium. So those are some of the key indications for knowing what the net force is going to be. Now, also for completion, let's go over the units. I don't think I went over that yet. F net is equal to ma. What is the units for mass? Kilogram. What about acceleration? What is acceleration? Okay, I'm hearing a lot of whispers, so there's a lot of lack of confidence in this class. Meters per second squared is correct. So the net force then has units of kilogram meter per second squared, which is defined to be what's called a Newton, capital N, Newton. All right, with all of this stated, now let's go over an example. So we're just going to do 2 examples and then call it a day. 2 examples. The first example I want to do is towing a car. Car, let's say, weighing 50,000 newtons. Now I'm just going to give this weighing means force of gravity. Which is Fg. Remember Fg, I gave this simple expression, is equal to mass times a gravitational constant g. So when we say something has a weight, we're talking about the force of gravity. So a car weighing 50,000 newtons is being towed up a 15-degree hill at constant speed. You're given friction is negligible. Let's say the tow rope is rated for 10,000 newtons. And the question that you're trying to answer is, will it break? Will it break? So you're towing a car uphill. It weighs 50,000 newtons and it's going up an incline of 15 degrees at constant speed. If friction is negligible and the tow rope is rated for 10,000 newtons, we want to know, is this rope going to break? So we begin by sketching a scenario. That is going to be our surface, that is going to be theta. we just sketch our car. So this would be the sketch, and alongside the sketch, we want to do what's called the free body diagram. So we are going to draw all the forces that are acting on our system. What is our system? What is our system? Right. No. That's a force. The system is what body of object are we considering?
The car. The wheels on the
Yeah, are we including the wheels? And the answer is yes, because it's moving as a collective unit. So everything here will be our system. Now, what are all the forces acting on the system? I'll do the hard one. Gravity. Yeah. What other forces are acting on the system?
In the last class, you made us tilt the free body diagram a little bit. Do we have to do that for a situation like this?
Well, let's see. Well, just
Okay.
tell me the forces. What other forces are there?
Tension.
Tension, which direction? See, now it's really hard. So we actually, like Sam was saying, we want to use a tilted coordinate axis where it's parallel to the surface. We define that as our x, and 90 degree to that is going to be our y. With this in mind, Sam, what direction is tension?
X.
Right, in the positive x direction, and that is why it is a benefit to use a tilted axis. It is absolutely not arbitrary, it is just directly along this line. Now, when you do this though, you would have to specify that as theta. Likewise, this is theta, that is theta, and that is also theta. Alright, so this is tension. What other forces do we have? Friction is negligible. Although, if there was friction, which direction would it be?
Would be acting downwards.
You mean like this?
Down slope. So the negative x.
Yeah, it would be negative x. If there was friction, it would be operating that, but the problem is directly telling us it is actually negligible. So we ignore it. Anything else?
Normal force.
The normal force, which direction?
Positive y.
Positive y is correct. The normal force, remember, is always perpendicular to the surface. Always perpendicular to the surface. Once again, another benefit of using the tilted axis. Because the normal force then goes directly along the x. Now, what do you know? Or, well, let's say, what are we given? We're given an angle theta, so we know that. We're also given 50,000 newtons, which is the force of gravity. What else are we given? Do we know anything else?
It's constant speed.
Meaning what?
Acceleration is 0.
V constant means acceleration is 0. Meaning what? Meaning what else?
F naught is 0.
It's an
Yeah,
equilibrium.
F net is equal to 0. Yeah. Equilibrium meaning F net is equal to 0. Well, we also see a value of 10,000 newtons. What is 10,000 newtons? What symbol do we give it? Or what is it?
Tension?
Tension? Incorrect. Is it because tension is restricted for the actual tension in the rope? Is this a number for the tension in the rope? And the answer is no, but it's the max. So we're given what is called the T max, the maximum tension allowed. And of course, we want to know what are we looking for? What do we want? We're looking for, will it break? Well, what is it?
The rope.
The rope. when will the rope break? Yeah, if we, it will break if the tension is greater than T max. Does that make sense? If it exceeds the maximum tension, then it will break. So, what is the question actually asking for? Not will it break, but what are we tasked with finding? No, T max is 10,000. 10,000 newtons.
Tension.
Yeah, we're tasked with finding what is the tension in this scenario. That is actually what we are after. Once we compute this, then we can actually give a meaningful answer to the question that is being asked. Now with the free body diagram, whenever you draw this, this is immediately, you can think of these two things as being married. Free body diagram is just going to scream Newton's second law. F equals ma. This immediately means to do that. Okay, those are paired so tightly knit together. Because a free body diagram tells you what all the forces acting are, and that's what net is. So net force is just all the forces acting together. So to answer this question, we begin with Newton's second law. F net is equal to mass times acceleration. Well, we look at what's given in the problem statement. We know that the acceleration is equal to 0. Therefore, this is equal to 0. The acceleration is equal to 0. So the right-hand side is taken into consideration. Now we just need to look at the left-hand side. Now what we're going to be doing is what is called the force balance. Force balance. Simply put, we're just asking, what are all the forces actually acting on our system? So we're just trying to expand out the left-hand side. In our scenario, what is the net force? Well, we have contribution from force of gravity. We also have contribution from tension, as well as, what is the last force? It will be the normal force. Our net force is actually consisting of these three vectors. And of course, we know that has to equal 0 because acceleration is equal to 0. Now, to do this problem, keeping it in vector form, that's not the way to go. We always want to break it down into the x and y components. So we first consider the net force in the x direction. It has possible contributions from force of gravity, tension, as well as the normal force N. And this is where the free body diagram is very, very important. You come here and you look. Tension is acting in the x direction, normal force in the y direction, force of gravity is kind of down at an angle. What are all the forces acting in the x direction? We have tension acting towards the positive or the negative?
Positive.
Right, towards a positive, so one of them will be positive T. Positive T. What about force of gravity? Does that have a x? Is that in the x direction? It's not exactly in the x direction, but it has a x component because what shape does that make? Why are you guys complaining? I told you guys how important trigonometry is. It's not like I didn't give you guys a warning. So we have what shape? Triangle. Right. We have a right triangle where this is force of gravity in the y, this is force of gravity in the x, and the hypotenuse is our force of gravity. And as long as you drew your free body diagram correctly, let me say, what I'm looking for in a free body diagram is everything in the black and green. So you should have at least one angle theta specified, as well as all of your forces in the correct directions. If you have that, that will be considered a complete free body diagram. That theta is important, okay? Where the theta is. As long as you drew it correctly, the theta will be up here. So we know force of gravity, that was at 50,000 newtons. So then what would be the force of gravity acting in the x direction? Remember, this is the x, so the force of gravity has a x-word component that way. You guys all see that? It has a x-word component. But what would that component be? Oh no, you guys didn't forget trigonometry, did you? Yeah, FG sine theta. This is opposite of our reference angle. So FG sine of theta. So there is a force of gravity term, and it is acting in the negative x direction, so it would be negative FG sine of theta. Now we look at the normal force. Does that have a x component? Does this, yeah, it's perfectly in the y, it does not have a x component. So this simply is equal to 0. Now this tension is what we were after. That's why it was smart to start along the x, because we see it's acting in the x direction. So we start here, and then we just assess. All right, we have an equation with it. Do we know tension? Well, no, that's what we're asked for, so it's okay not to know that. Do we know the force of gravity? Yeah, 50,000 newtons, we know that. Do we know theta? Yes, it's tilted at an angle of 15 degrees, and this is simply the problem. The tension is going to be Fg sine of theta, meaning it is 50,000 newtons times sine of 15 degrees. And if you do that, you're going to get a value of 12,940 newtons. That is tension. So are we finished? No. Why not? Yeah, make sure you actually answered the question. Okay, don't be like me. I lost a lot of points when I was in college because I got so happy I got a number. But then I forgot to actually answer yes or no. The question is a yes or no answer, or yes or no question with the answer representing if it will break. So what is your conclusion? Since T is greater than T max, it will break. So this is how the free body diagram is employed into using Newton's second law. Now let's slightly modify this problem before we move on to our second example. Question is, if instead of 15-degree hill, if it was on flat surface, the same question, will it break? So to do this, you have to start all over again. Draw our little sketch. It is on a flat surface. draw our little car. As such. And then we draw the free body diagram. What is this going to look like this time? You have force of gravity down. What else do you have? The normal force. This time the surface is flat, so we can use the typical XY Cartesian coordinate. That is left, right, and up and down. So the normal force is directly in the Y. What about tension? Which direction? Yeah, positive X. That will be T. And we have the same pieces of information. We're still looking for tension. So do you want to do X analysis or the Y analysis? Which one? Huh?
X.
Why? Alright, because that's where tension is, right? Yeah. So we want to do the force balance on the X. Force balance on X, F net in the X direction is equal to, what are all the forces acting in the X direction this time? What are all the forces acting in the X this time? Alright, there's a positive T, that's true, okay. Anything else? The answer is no. We know that this, according to Newton's second law, has to equal mass times acceleration in the X direction. What is the acceleration in the X direction this time? In this scenario? It's still moving at, where is it? Constant speed. If it's constant speed, then what's the acceleration? 0. Meaning tension is equal to 0. 0 newtons. And that's our final answer. Now, does that make sense? It literally takes no tension to pull a car forward at constant velocity. That makes sense? Alright, you try it. Are you guys serious? Do it. If you can do it without pulling tension on the road, automatic A.
Well, isn't that?
Actually, automatic Nobel Prize, because that likely you should win some prize. No, this actually doesn't make sense. So what's going on here? Well, let's answer the question. Will the rope break? Well, no, there's nothing acting on it. So therefore, not break. But the question is, how do we make sense of this? Well, let me give you two explanations. Right now, this really doesn't seem to make mathematical sense. It doesn't seem to actually represent reality, because I'm sure you guys have tried pulling a car, and it is not free. You actually have to do a lot of work to get it to move. The first explanation is on a flat surface, friction is the force that would have opposed in the X direction. So friction is the force in X that would have resisted. But what was one of our approximations? That friction was 0. But assumed F was equal to 0. F in the X direction was equal to 0. So that's one explanation. we actually got